Right now, as you lie in the dark and listen to these words, an invisible force is pinning you to your bed. It is the same silent power that keeps the planets locked in their orbits and makes entire galaxies dance in a cosmic ballet that lasts for billions of years. But here is the part that should really haunt you. After 400 years of scientific progress, after Newton, after Einstein, and after thousands of the most brilliant minds have dedicated their lives to it, we still don't actually know what gravity is. We can measure it with unbelievable precision. We can predict how a planet will move down to the millimeter. But its true nature? That remains a riddle that keeps the world's best physicists awake at night. You see, gravity is the only force in the entire universe that you cannot isolate. You can block light. You can shield yourself from radiation. But gravity goes through everything. It is always there, pulling, shaping, and bending the world around you. Think back to what you were taught in school. The story of the apple falling on Isaac Newton's head. It's a beautiful, simple, and comforting story. Newton told us that gravity is an attractive force between objects with mass. The more mass you have, the stronger the pull. The further apart you are, the weaker it gets. One elegant, logical, and predictable formula. For over 200 years, that was the end of the story. But there was a massive crack in this cozy image. Newton could describe what happened, but he never explained how it happened. How does the Earth know the sun is there, 150 million kilometers away? Between them, there is practically nothing, just a cold vacuum. How is the information about the sun's mass transmitted across that emptiness instantly? Newton himself admitted this was a total absurdity. He understood that his theory was just a description, not an explanation. He knew how to calculate the force, but he remained silent on the nature of the force itself. Then came Albert Einstein. In 1915, he flipped the script and suggested something so radical that many scientists didn't even believe him at first. Einstein said that gravity isn't a force in the traditional sense at all. Gravity is geometry. Imagine a stretched rubber sheet. If you place a heavy bowling ball in the middle, it creates a dip, a curve in the fabric of the sheet. Now, if you roll a small marble across that sheet, it won't move in a straight line. It will roll into the curve created by the bowling ball. From the side, it looks like the big ball is pulling the small one. But there is no invisible tether. There is only the warped shape of the surface. Einstein proposed that this is exactly what massive objects like stars and planets do to the very fabric of space and time. But this leads to an even deeper mystery. If gravity is the curvature of space-time, then what exactly is being curved? Space and time aren't physical objects you can touch. They aren't made of matter. And yet, they can bend, stretch, and ripple. It sounds more like mysticism than physics. We've even seen proof of this rippling effect. Einstein's theory predicted gravitational waves, ripples in the fabric of space-time that travel at the speed of light. When two black holes collide, they send shudders through the entire cosmos, stretching and squeezing space as they pass. In 2015, we finally detected them, exactly as predicted. But even with this triumph, the conflict remains. Our two most precise theories of the universe, general relativity for the big stuff and quantum mechanics for the tiny stuff, are in total contradiction when it comes to gravity. When we try to apply quantum math to gravity, the equations blow up. They produce infinities that make no sense. This means we don't have a quantum theory of gravity. We don't understand how gravity works at the smallest scales, like the heart of a black hole or the very first moments of the Big Bang. We're looking at a reality that is fundamentally incomplete. One of the most mind-bending consequences of Einstein's theory is that gravity doesn't just warp the space you move through, it warps time itself. Most of us think of time as a universal constant, like a giant, invisible clock in the sky that ticks exactly the same for every single person in the universe. But gravity shatters that illusion completely. The rule is simple and brutal. The stronger the gravitational pull, the slower time flows. This isn't just a theoretical trick used by physicists to fill up chalkboards. It is a reality that we have to deal with every single day of our lives. If you use the navigation on your smartphone, whether it's GPS or GLONASS, you are using a technology that has to account for the fact that time is literally moving at a different speed high above your head. GPS satellites orbit about 20,000 kilometers above the Earth's surface. Up there, the Earth's gravitational field is significantly weaker than it is down here on the ground. Because of this, according to the general theory of relativity, the atomic clocks on those satellites actually tick faster than the clocks on your wrist. The difference is tiny, about 45 microseconds per day. It sounds like absolutely nothing, right? But if engineers didn't use Einstein's equations to correct for that tiny shift, your GPS navigation would be off by several kilometers within a single day. Every time you find your way to a new restaurant or track a delivery, you are witnessing a practical, real-world application of the curvature of space-time. But you don't need to go to outer space to see this. Scientists have measured this effect on much smaller scales. Using ultra-precise atomic clocks, researchers have registered differences in the flow of time between devices placed only a few dozen centimeters apart. You heard that right. Clock sitting on your kitchen table is ticking slightly slower than a clock on the shelf right above it. This leads to a disturbing realization. Time, which feels so absolute, is actually fragmented. Because your head is further from the center of the Earth than your feet, your head is technically aging faster than your feet. Over a 70-year lifetime, the difference is only about 1/1,000,000th of a second, but it is real, it is measurable, and it proves that there is no such thing as a universal time. Every point in the universe has its own unique time, and those times are woven together by the invisible threads of gravity. But why does this happen? Why is gravity so deeply linked to time? This is where our understanding of the universe hits a massive wall. We have two great theories: general relativity, which describes the big stuff like stars and galaxies, and quantum mechanics, which handles the tiny world of atoms. Problem is that they are in a state of total war when it comes to gravity. This isn't just a philosophical disagreement. It is a mathematical contradiction. When physicists try to apply quantum math to gravity, the equations blow up. They produce infinities, results that make no sense in the physical world. For other forces, like electromagnetism, we solve this with a trick called renormalization. But with gravity, that trick simply doesn't work. This means we don't have a quantum theory of gravity. We don't understand how gravity behaves at the smallest possible scales, at the Planck length, which is billions of times smaller than an atomic nucleus. This missing piece of the puzzle is critical, because the Planck scale is where the most dramatic events in the history of the universe take place, inside the hearts of black holes and in the very first moments after the Big Bang. Our inability to merge these two theories means we literally do not understand how the universe began, or what truly happens when matter is crushed into a singularity. We can see the effects of gravity. We can use them for our satellites, but the core mechanism remains a black box that we haven't been able to unlock for over a century. We are staring at a reality that is fundamentally incomplete, and as we are about to see, the ghosts of the cosmos are only making things weirder. If you think gravity on Earth is strange, wait until you see what it's doing on a scale that defies human imagination. When we move beyond our solar system and look at the vast architecture of galaxies, the story of gravity becomes even more haunting. Back in the 1930s, a Swiss astronomer named Fritz Zwicky was studying massive clusters of galaxies. He was measuring the speeds at which individual galaxies were moving within those clusters, and based on those speeds, he tried to estimate the total mass of the group. The result left him in a state of total disbelief. The galaxies were screaming through space much faster than they should have been. According to the amount of visible matter, all the glowing stars, gas, and dust, there simply wasn't enough gravity to hold the cluster together. By all rights, cluster should have flown apart eons ago. Zwicky hypothesized that there must be some invisible, hidden mass providing extra gravitational glue. He called it dark matter. At the time, many in the scientific community thought he was just making a bold, perhaps even desperate, guess. But then, in the 1970s, an American astronomer named Vera Rubin hit the same wall, this time within individual galaxies. She was studying rotation curves, how fast stars move around the galactic center. According to the laws of Newton and Kepler, stars at the very edge of a galaxy should move much slower than stars near the middle, just like Pluto orbits the Sun much slower than Mercury does. But Rubin discovered something impossible. The stars at the jagged edges of galaxies were moving at almost exactly the same speed as the stars in the center. It was as if a record was spinning at a constant rate, even though the stars at the edge had no physical reason to stay attached. The only way for those galaxies to stay intact was if they were surrounded by a massive, invisible halo of matter that we simply cannot see. Today, dark matter is one of the greatest mysteries in all of science. We know it exists because we see its gravity pulling on everything, but we have no idea what it is. It doesn't emit light. It doesn't reflect light. It doesn't absorb light. You could shine a billion suns at it, and it wouldn't cast a shadow. It passes through regular matter, including your own body, like a ghost through a wall. Think about the implications of that for a moment. About 85% of all the matter in the entire universe is this silent, invisible stuff. We, and everything we have ever seen, every star, every planet, every human life, are just a rare, exotic 15% minority. We are living in a universe that is dominated by a presence we can only detect through its gravitational heartbeat. But the story gets even more unsettling. In the late 1990s, astronomers studying distant supernovae stumbled upon a discovery that turned cosmology on its head. Since the Big Bang, the universe has been expanding. Scientists assumed that gravity, collective pull of all the matter in the cosmos, would eventually slow that expansion down, much like the Earth's gravity slows down a ball you throw into the air. But they found the exact opposite. The expansion of the universe isn't slowing down, it is accelerating. It's as if the ball you threw into the air suddenly grew rockets and started flying away faster and faster. We named this mysterious force dark energy. If dark matter is the cosmic glue, then dark energy is a kind of anti-gravity that is pushing the very fabric of space apart. Consider the cosmic budget. Ordinary matter is 5%. Dark matter is 27%. Dark energy is 68%. We understand only 5% of what our universe is made of. 95% of reality is a complete and total black box. And what's even more disturbing is that dark energy is slowly winning the war. As the universe expands, matter gets spread thinner, but the density of dark energy remains the same. Billions of years from now, dark energy will push other galaxies so far away that their light will never be able to reach us again. The observable universe will shrink until our local group of galaxies is surrounded by an absolute, frozen, and terrifying void. Every other light in the sky will simply vanish into the darkness. One day, the last stars will flicker out, and the universe will transform into a cold, empty, and eternal abyss. We call this the heat death of the universe, cosmic tragedy where gravity and its mysterious antagonist, dark energy, play the final, silent roles. After seeing how gravity can warp time and hide 95% of the universe, you'd think it was the most powerful force in existence. But here is the most baffling contradiction in all of physics. Gravity is actually the absolute weakest of the four fundamental forces. It is so weak that it feels almost absurd to even call it a force when compared to the others. The electromagnetic force between two protons is roughly 10 to the power of 36 times stronger than the gravitational attraction between them. That is a 1 followed by 36 zeros. If the pull of gravity between two particles was represented by a single second, the electromagnetic force between them would last longer than the entire age of the universe. Physicists call this the hierarchy problem, and it is a massive hole in our understanding of reality. Why is there such a terrifyingly large gap? Why does gravity barely seem to register at the atomic level while every other force is screaming? Some theorists have proposed a mind-blowing explanation. Maybe gravity isn't actually weak. Maybe we are just seeing a tiny fraction of its true power. This is where string theory enters the room with its 10 or 11 dimensions of space. The idea is that the other three forces, electromagnetism and the nuclear forces, are trapped on our three-dimensional membrane of reality. They can't leave, but gravity might be unique. It might be the only force that can leak into extra, hidden dimensions that we can't perceive. If gravity is spreading its strength across 10 dimensions instead of just 3, it would explain why it feels so thin and lightweight in our world. We might be living on a thin sheet of paper, watching the shadow of a force that is much more powerful in the bulk of the cosmos. But even if we accept this, we still hit the quantum wall. Every other force has a messenger particle that we've already discovered, the photon for light, gluons for the nucleus. But the graviton, the hypothetical particle of gravity, remains a ghost. And it's not just that we haven't found it, it's that our math breaks when we try to invent it. When you try to combine Einstein's smooth geometry of space-time with the jittery, pixelated world of quantum mechanics, you get infinities. The equations literally give you nonsensical results that can't be fixed. This means that on the smallest possible scales, Planck length, we have absolutely no idea what is going on. This mathematical failure is why we can't fully explain the life and death of stars. Inside a massive star, there is a constant, violent war. On one side, gravity is trying to crush the star into a single point. On the other side, nuclear fusion is creating an outward pressure that holds the star up. For millions of years, it's a stalemate. But eventually, the fuel runs out. Once the star starts producing iron, the fusion stops giving off energy and starts consuming it. In that split second, gravity wins the war. What happens next is one of the most brutal processes in the universe. Core of the star collapses at 1/4 of the speed of light. The outer layers crash inward, hit the ultra-dense core, and bounce back in a gargantuan explosion, a supernova. This single event can outshine an entire galaxy for weeks. If the star was massive enough, it leaves behind a neutron star, an object so dense that a single teaspoon of its matter weighs 1 billion tons. Gravity here is so strong it bends light into circles, allowing you to see the back of the star while looking at the front. But even a neutron star isn't the final limit of gravity's hunger. If the core is heavy enough, nothing in the known laws of physics can stop the collapse. Gravity continues to crush everything until the very fabric of space and time rips open. You are left with a hole in the universe. A place where time stops and the quantum wall becomes a total barrier to our understanding. We have arrived at the event horizon. And as we are about to see in our final act, this is where gravity stops being a mystery and starts becoming a nightmare. To see gravity at its most terrifying, we have to look at the monsters lurking in the deepest reaches of the dark. Black holes. These aren't just very dense stars. They are actual, physical tears in the fabric of space and time. When a star 25 times more massive than our sun dies, gravity wins its final, brutal battle and crushes the star's core into an infinitely small point called a singularity. Around this point, a boundary forms called the event horizon. This is the point of no return. Once you cross this line, not even light is fast enough to escape. To get out, you would have to travel faster than the speed of light, which Einstein proved is physically impossible. At the very center, curvature of space-time becomes infinite, and the laws of physics, as we know them, simply stop. But even these cosmic giants lead to a deep paradox. Stephen Hawking showed us that black holes aren't truly black. They slowly leak radiation and eventually evaporate. This creates a massive problem for science, the information paradox. If a book falls into a black hole, and that black hole eventually disappears, where did the information in that book go? If it is lost forever, our entire understanding of the universe is broken at its foundation. Now, take a step back and look at the entire universe. Gravity is the sculptor that carved the cosmic web. Galaxies aren't just floating randomly. They are gathered into clusters and filaments by gravity, like a giant spiderweb made of light. Our own Milky Way is currently screaming through space toward a mysterious gravitational anomaly called the Great Attractor, 250 million light-years away. We are passengers in a massive cosmic current, being pulled toward an unknown destination that we can't even see. But what is the final act of this drama? Gravity created everything. It ignited the first stars and shaped the planets. But it is also the ultimate executioner. Through dark energy, the universe will continue to expand until every star burns out and every black hole evaporates. We call this heat death. In the end, there will be nothing left but a cold, empty void. Time itself will lose its meaning because there will be no events left to mark its passing. It's a heavy thought, isn't it? But there is something beautiful in it, too. You are a direct product of gravity. Carbon and iron in your blood were forged in the hearts of stars that were crushed by gravity billions of years ago. When those stars exploded, they scattered their dust across the void, and gravity gathered that dust once again to form the Earth, and eventually, you. We are stardust organized by gravity into thinking, feeling beings. We are the universe trying to understand its own mysteries. And even though we don't have all the answers, even though gravity remains a riddle we can't solve, the act of asking the question is what defines us.